All right, what's the chip of the day? The chip of the day is a 2N5457, otherwise known as a JFET. Okay, it's a JFET transistor. And I chose this particular JFET transistor because I have a lot of them, and it's a very, very, very common one. So JFET transistors are well known for their high impedance input. They're used for front-end preamplifiers, measurements, electrometers, microphone preamps. Anytime you need a very, very high input impedance, JFETs are your friend. So we'll be taking a look at this. They are not a high current device. They're a very low current device, but they are very good at what they do, and nothing can really beat them. Okay, we're going to be looking at this circuit here. And if you're familiar with LEDs and you are familiar with regular FET transistors, you say, well, you can't do that. If you turn this on, you'll blow up your LED. If that's true, if you put an N-channel MOSFET in here, an N-channel MOSFET is just basically going to be like a relay, and that's going to turn on hard. There'll be like maybe 0.02 ohms of resistance, and it'll short this thing to ground, and that'll put however many amps your 12-volt supply has in it. It'll go through that diode, and it'll blow it up. So JFETs are completely different, though. Okay, so we're talking about JFETs. All right. JFETs are not like other FETs. Let me draw a little picture over here. So if this is kind of a material science diagram of a JFET, okay, the current's going to come in here through like this. It's got to go through this bulk material, okay? So this is some kind of bulk material, it's silicon, okay? And the charge is going to go through that bulk material. Now, it's not a very good conductor, though. It doesn't conduct very well at all. In fact, the data sheet has it about 1 milliamp. Okay. So really, it only passes 1 milliamp, and it won't do any more than that, right? But you can make it do less than that. So JFETs are completely backwards. NPN transistors and PNP transistors, bipolar transistors, if you add more current, they will conduct more current. And FETs, generally, the higher the voltage, the more current that flows in them. But JFETs are just the opposite. You put voltage on the gate. Okay, so this is a gate, drain, and source. And you put voltage on this gate, and it will turn off the transistor. It won't turn it on; it'll turn it off. It works just the opposite. And you can think of it as you start putting a voltage on the gate, and what happens is it'll generate this electric field around the gate. You'll put a charge on the gate here, and it'll build up this electric field, and it basically pinches off the conduction path. So you used to have a nice wide path for the the current to go through, but now you have this really, really narrow path for the current to go through. And in fact, if you have a big enough voltage, you can have it pinch off entirely, and then it won't conduct at all. Okay. So let's look at the diagram that shows that in the data sheet. And it's this one here. And this is the gate to source voltage. That's the voltage from here to here. And as you start out with 0 volts, so if the gate is 0 volts, then it will have the maximum conduction. That means that you will have no fields in here at all. It'll allow this thing to pass. And we'll have about 1.1 milliamps of current flow. All right? And then as we change the gate voltage to minus 0.4, minus 0.8, minus 1.2, we put a voltage in here, but it's a negative voltage. And as we increase that negative voltage, we'll have less and less current flow. So if we want 0.6 milliamps. If we started at 1 milliamp and now we want 0.6 milliamps, we need to put in about minus 0.3 volts, okay? And it keeps going down and down and down. So finally, when you get to about minus 1.2 volts, that's the cutoff voltage. That's when it pinches off entirely and you'll get no current flow at all, all right? So let's go ahead and test that on an actual circuit, all right? We'll actually see if we can reproduce this graph with an actual circuit. And again, the maximum it can draw is about 1 milliamp, but we can make it go less and less and less. So here's the circuit. I've got a LED in there, and the LED is glowing. And guess what? It's glowing at 1 milliamp, and the gate voltage is 0 volts. I have it connected to ground, so the gate voltage is 0. And so this JFET is sending as much current as it knows how through the device. So let's grab a power supply so we can change the gate voltage, and we will input negative voltage. So I'm going to hook the positive lead up to ground. The negative lead is going to go on the gate, all right? And it lit up, and I'm outputting 0 volts. So now I'm going to increase the voltage, and you can see that LED goes dimmer and dimmer and dimmer, right? And let me kill the room lights here so we can see that a little bit better. Maybe that's too much room light gone. There we go, that's better. All right, so I'm gonna go down to 0 volts, and it's the very brightest. I'm gonna go down to, let's see, this is 0.2 volts. 0.3 volts is the negative 0.3 volts. Negative 0.6 volts. Negative 0.7 volts. Negative 0.85 volts. It's getting very, very dim now. Minus 8.6 volts. So you can see that we can actually change that. So let's go ahead and put some voltmeters on here so we can see what's going on. All right, there we go. So the very maximum is, this is microamps, so we can go to milliamps. 1.1 milliamps, that's as 1.2 milliamps. That's as much current as this thing can do, okay? Then let me change my power supply to, this is minus 2.5. We're only getting 646 microamps now. Let me increase it to 0.3. 0.42. Let's go up a little ways. Here's minus 0.62. Well, down to 111 microamps. Let's go to minus 0.77, 17 microamps. And then let's go up to that minus 1.2 volts. And yeah, it's turned off, 0.02 microamps probably. No more microamps left. Let me disconnect the microamp meter. Yeah, we're at 0. So there's a little bit of offset on the display here. But there you go. We are able to vary the amount of current that the JFET transistor will conduct. Okay, so what we've seen is if we change the gate, then the amount of current changes. So if we wiggle voltage here, we will wiggle current over here, right? So wiggling voltage here equals wiggling current here. And if we change the LED, get rid of that, and we put in a resistor, then if we have a wiggling current, we will generate a wiggling voltage on the resistor. So wiggling voltage equals wiggling voltage. That's an amplifier. So let's take a look at an amplifier. All right, so here's the amplifier we're going to be taking a look at. so this is a self-biasing amplifier. And so how did I do the component selection? Well, I chose this part because it seems to be popular. There's two FETs that I have in my drawers. The 2N5457s, I see a lot of those in different circuits. And I have J310. And those two seem to be quite popular FETs. Now, I had somebody ask me about how do you choose the right one, and I don't know. Honestly, I don't know. I know that some of the FETs are low noise. I know that some of the FETs are very, very low current, like less than a picoamp of current. So if you have a real critical measurement to make, you would choose one of those. Now, my circuit, I'm not too worried about that because I've already killed my input impedance. My input impedance is now 4.4 megohms. If you were designing a circuit like this and you needed more high impedance, you could put different resistors here. A lot of microphone circuits that look like this, a lot of microphone circuits will put a 1 gigohm resistor in here. 1 gigohm resistors are quite expensive, so you have to want to use one, right? And in generally medium grade circuits, you see a lot of 1 meg. A lot of 1 megohm resistors. 1 meg is just fine. I looked at my parts bin, and this is the biggest one I had in quantity, so that's what I put in there. So that's how I chose that one. How did I choose the capacitors? Well, of course, they're my favorites, 0.01. They're not too critical. If you wanted this to be really, really broadband, you could put in, 10 microfarad on these two. It doesn't really matter. The 10K, again, favorite resistor. In these circuits, if you're operating, around 12 volts and stuff, 10K is just really, really standard. There's really not much going on in that resistor, nothing really to worry about. The only resistor to worry about in the circuit is the 270, and this is the one that I had to choose, okay? And so I need to talk a little bit about how did I choose this resistor. Well, because this is self-biasing, all right, you want to have the gate at a negative voltage to the source. And so you need to look at the data sheet and figure out what value of voltage you really need. So let's look at the data sheet. This is for the 5457, and I looked at this graph here, okay? And this is drain to source volts, and we're going to be in the middle here somewhere, so it doesn't matter. The thing that I need to worry about is which one of these curves do I want to be operating on? And you can see that the spacing of these two and the spacing of these two is about the same. And then they get closer together, and they get closer together, and they get closer together. What does that mean? Well, it means that if you wiggle back and forth, you're going to be wiggling back and forth in this direction. The input is going to change up and down. And if you're changing up and down and these distances are about the same, that means that you're going to have equal amounts of output change for input changes. Down here, you will have a bigger output change in the up direction and a lower one in the down direction. You'll start to compress. This might be a good way to build a audio compressor, is to operate your FET down in this range. But anyway, that's not what I want. I want to be in the linear range. I want to be where they're kind of equally spaced. So either that line or that line is probably okay, but I'm going to want to be right in the middle here. And so what I said was, okay, I want to be 0.2 volts. This is negative 0.2 volts. And that's going to equate here to about 0.7 milliamps, okay? That's where I want to be operating. I'm going to set my operation point right about there. And so how do I get negative 2 volts on the gate? How is that possible? How do I get negative 2 volts? I only have plus 12 in the system, so how do I get negative 0.2 volts? Well, all right, so I'm going to have plus 0.2 volts here, and I'm going to have 0 volts here. And the differential between these two, it's plus 0.2 volts in this direction, but in this direction, the opposite direction is going to be minus 0.2 volts. So we're going to have effectively minus 0.2 volts across the gate to source, okay? So I want 0.2 volts here. Well, how do I get 0.2 volts here? Well, remember, I want 0.2 volts and I want 0.7 milliamps, okay? So voltage equals current times resistance, okay? So my voltage is 0.2, my current is 0.7, and we have to calculate R. So we'll get out a calculator, we have 0.2 volts, and we divide that 0.7 milliamps, and we get 285 ohms, okay? So the calculation says I need 285 ohms. And I looked in my sorted bins, and 270 was as close as I could get. So we're going to have 270. Now what's that going to equate? Okay, so we can calculate that. If we had 0.2 volts, let's see, if we had 0.7 milliamps, and we had 270 ohms, we would have 0.19 volts here instead of 0.2. So, you know, we're within 10% or 5%. We're within 5%. So we're doing really good. All right. So that's how I chose that resistor. Another way to choose the resistor is just copy somebody else. Look in a book, find a circuit, copy what they did. Okay. But anyway, that's the way it's done, is to kind of get here in the middle somewhere and do the calculation. You'll get 270 volts, ohms, sorry. So let's hook this up and see what it does. All right, I have it over here. It's piled in a bunch of clip leads and everything. I have sources going in. I have 2 scope probes, and I have voltages and everything. But the little transistors down there and stuff. So let's see how it's doing. And there we go. The cyan trace is the input, and the yellow trace is the output. And there's gain. Let's see here. Let me make sure everything is equal here. This is 0.5 millivolts per division. Let's change this one to 0.5 millivolts per division. There we go. Oops, get the trigger down here. So there you go. This is our input. That's our output. So we have quite a bit of gain. It looks like about 10 to 1 maybe. And so we're doing really good. All right. I know a lot of people are going to hate this. How much gain do we have? How do we do that calculation? It's kind of an ugly calculation. I don't care. So a lot of people are going to say, well, you have to know mathematics and you have to understand all these equations and everything to do anything, to be an engineer, to build circuits. You got to know it. To get a fundamental understanding, you got to know all that stuff. Well, I'm going to use this thing as an amplifier, all right? And I kind of hooked some things up, kind of by looking at what other people had done, and kind of by doing my own calculation and everything, okay? And this is what I ended up with, okay? I ended up with a gain of 10. Now, if I need more, I'll just follow this up with an op amp, because now I can use an op amp because it's nice and big, right? Why did I use a JFET? Why did I use a JFET? To have a very, very high impedance input node, right? If this is like a 1 gig ohm resistor, I have a very, very high impedance. Well, everything you do after that, you know, you're going to have lots of current out here. You're not going to have to worry about it. You're not going to affect your measurement, right? And so whatever gain I have here is going to be fine in my circuit, okay? If I have a gain of 10, great. If I need a gain of 20, I'll follow it up with a gain of 2. If I needed a gain of 5, I'll just put a resistor divider on it and just knock this down, right? Do I really, really need to calculate the gain? Well, sometimes you do. And sometimes you'll have to go look at that ugly equation and you'll have to go figure it out. But I'm not going to do it. I'm just not going to do it because I don't need to do it, right? So don't worry about needing to know everything, because a lot of times you don't, especially in the garage. You just need something that works. And this is going to work absolutely perfectly. Now, the other thing that you might see in circuits like this is, remember that 0.2 volts? That was the DC biasing of everything. It had nothing to do with the AC path. It was the DC biasing. Well, what if we did this? Okay, you'll see this in a lot of NPN circuits, NPN transistor circuits. Just a lot of times you'll see this capacitor put here, and that means that the AC sees a much lower resistance. The AC previously saw 270 ohms, but now the AC is going to see a very, very low, low ohms, right? And in a NPN transistor setup, the gain is kind of this resistor divided by this resistor. And if you put in a capacitor here, you basically throw that resistor away. And now you're relying on the base to emitter resistance. But FETs don't work that way. JFETs don't work that way. But by putting this capacitor in, it does work the same way. It does increase the gain in a slightly different way physically, but effectively it does the exact same thing. So what we're going to do is, okay, let me go back down here. I'm going to insert a 10 microfarad capacitor, okay? 10 microfarads. Make sure you put the little plus thing over there. All right, so we're going to have 10 microfarad added to the circuit. And let's see what that does. Just bring over the camera. All right, here I'm going to add it. And look at that, it goes up. So how much did we gain? If this was a gain of 10, maybe now this is maybe a gain of 15 or something, right? And so adding that capacitor definitely increases the gain. And then you can kind of convince yourself, do I need it or not, right? Do I actually need that part or not? In your circuit, you might. In my circuit, maybe I don't. So it's something you can put in if you like, but certainly not required. Okay, that was the tip of the day, the 2N5457 JFETs, a very brief introduction to what JFETs do. I am no expert. JFETs are kind of little strange devices, and the mathematics of the gain calculations and stuff is kind of weird. I didn't want to go into that today. Yeah, you will see them a lot. I did a really, really nice series on microphone amplifiers, and I'll put some links down below. If you want to see more about JFETs and how they're used, I looked at a Neumann circuit and I looked at a Rhodes circuit that was a clone of the Neumann circuit. And it uses JFETs in the preamplifier, and it uses them as a current source. And I think it uses them and a cascode amplifier. Two JFETs wired a really strange way to create a cascode amplifier. So yeah, lots of really, really clever JFET things going on in those videos. So like I said, I'll link those down below.